In the last video, we were talking about proving the unique existence of length measure on RB. That is, we have this measurable space and we want to show that the concept of length that we have been using all along from our childhood really exists in a well-defined way and is unique. Now, typically we do not talk about the length measure in mathematics. We have a different name for it. We call it the Lebesgue measure. Now let's understand what is meant by this unique existence. That is to show that there is a unique function mu, whose domain is the Borel-Sigma algebra to this extended 0 to infinity, such that whenever you take any closed interval, then the length of that is what exactly we expect it to be. And mu is countably additive, that is, if you take countably many disjoint sets in B, then the union will have length given by the sum of all those individual sets. Now, once you have countable additivity and this result, you can immediately see that even if I make it open, it remains B minus A, because by taking A equal to B, you can prove that singletons have length 0. So I can remove a singleton by countable additivity and I can get open here, open here, open in both sides. And also I am talking about AB in R, so infinity has not been included here. But again, thanks to countably additive thing, if this holds, then if I make one of them infinity, A to infinity, this open interval unbounded, then this will become infinite. Now the proof that such a thing exists uniquely proceeds in 3 steps. Now we start not with the entire Borel-Sigma algebra, which is complicated, but with just this script D, which is set of all intervals in R, and that includes the bounded intervals, unbounded intervals, open, closed, semi-open, semi-closed, and all those stuff. And on this set, which is much more easily describable, we define mu1 as the usual length. So for all these possible types of intervals, it is just the length. Similarly, for all the unbounded intervals, it is the symbol infinity. So you can see the advantage of working with script D instead of working with the entire Borel-Sigma algebra. For script D, we have a nice description of all its elements. But for Borel-Sigma algebra, we do not have a clear such description for all the things. So here I could manually define all this stuff. Now the first thing that I will do is show that this mu1 has the necessary property. That is, mu1 is countably additive on script D. That is, if d1, d2, etc. disjoint and the union is in script D, earlier we did not have to put this condition when we worked with the sigma algebra because it was guaranteed, but now that's not guaranteed, then this result will hold. For example, if I take my countable collection d1 to be 0, 1 and d2 to be 100 to 200, then of course this thing is not an interval. So in order for this to be yet in script D, the things must be all side by side. Then this will be this result. Now here we are not going to embark upon the detailed proof. I am just giving the basic outline. So in step 1, we have to prove this. So mu1 is our first approximation to the target mu. In step 2, we enlarge our collection of sets. We are going towards the Borel-Sigma algebra. Script F, set of all countable unions of intervals in R. That is, we take elements from script D and then we take countable unions of them. Clearly, our script D is already there because countable union definitely means just finite. If I take only one interval at a time and take union of that, then I get back the interval itself. So script D is already inside script F. Then we can extend this mu1 whose existence we saw, not existence, we just constructed mu1. We can extend it uniquely to a mu2 from script F. The precise definition is there exists unique mu2 such that script F from script F to the extended line such that if you restrict mu2 onto script D, that is the restriction notation, then it is mu1. Now of course you can always just extend anything you have to put the condition and mu2 is also countably additive. So there is only one unique extension of mu1 to a countably additive functions from script f to 0 infinity. Now again, we are not going to prove it here, but I am just giving the basic outline. Now in the final step, we consider our target, the Borel-Sigma algebra. Clearly our script f is inside Borel-Sigma algebra, so we want to lift mu2 to something in script b, something defined on script b, and that will be our target Lebesgue measure. So as usual, we have a theorem, much like theorem 2, which says there is unique mu defined on script b, taking values here, such that mu extends mu2, that is, if you restrict mu to script f, that's the restriction sign, then you will get mu2, and of course, we need a condition on mu is countably additive. There is only one way of extending mu2 to entire script b, and it is this mu which will be the Lebesgue measure. Now we have got three theorems, none of which we have proved. Theorem 1 is very specific to the length measure, but theorem 2 and theorem 3, it turns out, can be generalized. The argument can be used for other measures also, and we shall discuss the statements of the generalized version in the next video.